Dear students, till now we have covered all the points from point 1 to point 12. Okay, today we'll see problems and solutions. To solve the problems, we'll see what are the equations till now we have come across. One is the output equation Q is equal to C naught D square lns. Okay, D is the diameter, L is the length, ns is the synchronous speed in RPS. This is output coefficient C naught is given by 1.11 pi square B average AC into kW into 10 raised to minus 3. Okay, and sometimes this, if you multiply, you'll get L. Okay, volume of the machine, the square L, you can get using this equation Q by C naught ns. Then how to separate D and L? So here for round poles we have to use L by 2 ratio 0.6 to 0.7, and for rectangular poles L by 2 ratio is equal to 1 to 5. Okay, so higher the value, cheaper is the machine. So now here you can see another factor how to select L by 2 ratio. L by 2 is equal to L by 2 is nothing but pi d by P. So this L by 2 is equal to L into P divided by pi d. So now here, as D increases, L by 2 ratio decreases. L by 2 decreases. Okay. If diameter is large, L by 2 ratio is less. If diameter is less, L by 2 ratio is large. So here we have to select from 1 to 5. Okay. Deciding factor for the diameter is the peripheral speed. Okay. So what should be the maximum size of the diameter? D. So this peripheral speed, it decides the diameter of the rotor. Okay. So now here peripheral speed for bolted on pole construction should be less than or equal to 50 meter per second square per second. So for dovetail and T-head construction, VA should be less than 80 meter per second. I told why it is. Okay, this is a little bit strong construction. Here construction is a little bit weak. Okay. Now next, coming to length of air gap, LG can be found out using this equation. LG is equal to ATG divided by 8 lakh kg BG. So ATG is usually 70 to 80% of ATF naught. Okay. So now what is ATF naught? ATF naught is nothing but SCR into ATA. How to find ATA? ATA can be found out using this equation. So find this ATA. Substitute here SCR you have to select, and here 0.7 or 0.8 substitute kg bg, you will get length LG. Okay. Now to select slot pitch YS, some guidelines has been given. YS should be less than or equal to 25 mm for low voltage machine. YS should be less than 40 mm for 6 kV or low voltage machine. For silent pole machines, slots per pole per phase, that is QS, should be equal to 2 to 4, usually 3. In case of turbo alternators, number of slots per pole per phase QS, that is equal to 7 to 9. The number of slots per pole per phase also be taken as fractional numbers such as 3.5, because it reduces the magnitude of higher harmonics in the EMF wave. Instead of 3, we can take 3.5. Another guidelines, the slot loading should not exceed 1500 amps. Slot loading means conductors, number of conductors multiplied by current in the conductors. Okay. Now how to find out turns per phase? This is the basic equation. EPH is equal to this. This is the turns per phase. So here pi is nothing but pi m is here. This one pi m. Okay. Pi m is nothing but B average into tau n. So if there are a number of parallel paths, then EPH is equal to this equation, TPH by FKW. So TPH is found out using this equation. Once you find out turn per phase, now we'll see a cross-sectional area of the conductor. For that you should find out current, phase current. Okay, kVA into 10 raised to 3 divided by 3 EPH. This is 3 phase power EPH into IPH in terms of kV. So now is that the current in the conductors IPH by A. There are a number of parallel paths. So area of the cross section of the armature conductor AS is given as IZ divided by delta S. Delta S usually 3 to 5 amps per mm square. That is current density. Finally, resistance per phase of armature winding Rs is equal to rho Lm Ts. Ts is a turns per phase divided by cross sectional area. It will give resistance per phase. And you can find out copper loss also 3 I square S Rs. Okay. Now coming to design of field system. Now design of rotor of silent pole machine. Okay. So flux in the body pi p is equal to leakage coefficient, that is CL, and useful flux per pole pi. So CL is usually 1.15 to 1.2. So the area of the cross section of the pole body is given by like this. BP you have to assume. BP is equal to 1.5 to 1.7 Weber per meter square. So once you find out area also can be found out using this equation. Also we know that area is equal to AP is equal to BP into LPI. The width, this is length, net iron length, where LPI is equal to L into KI, net iron length. So length, the length of pole is taken as LP is equal to armature pole length, BP width of the pole, KI stacking factor, it is usually 0.98, L is armature length. Okay. Now for circular pole, this is circular pole, dp is the diameter, area of the pole is equal to pi by 4 dp square. dp is the diameter of the pole. Okay, this is not square pole. Okay, this is it looks like a rectangular pole. This is rectangular pole. Okay, this is rectangular pole. This is circular pole. Now to find out height of the pole, so already this derivation we have discussed in DC machine. Okay, so to counterpart armature reaction, the ratio ATFL by ATA should be 1.7 to 2. So this implies ATFL is equal to 1.7 to 2 times ATA. So ATA is found out using this equation. This is the basic equation. So once you find out ATA, substitute here, ATFL you find out. And height of the field coil is found out using this equation. Substitute ATFL here, SF, DF, QF, all we know, and you can find out height of the field coil. Once you find out height of the field coil, substitute here, height of the pole can be found out by adding this insulation. Okay. So now depth of the rotor core is equal to flux in the core section pi c is equal to half of this. In the core, flux will divide half of the pi p. Pi p is this, half of the CL into pi. So cross sectional area of the core is equal to AC is equal to pi c by BC, that also equal to LC into DC. This is depth of the core. Okay. So AC, now this BC we assume, pi c we know, pi c we have calculated here. AC you can find out. So this we know and LC we know. Depth can be found out. Depth of the. So now depth of the core is equal to AC by LC. Okay, where LC is equal to LP high. Here BC what we are assuming 1 to 1.5 Weber per meter square. Now coming to calculation of MMF per pole at no load and normal voltage. So MMF per pole at no load and normal voltage is calculated using this equation. ATF naught is equal to ATG, ATT, ATC, ATP, ATY. Ampere turns requires for gap, ampere turns required for stator teeth. Okay, ampere turns required for this core. This is for pole, this is for yoke rotor, yoke. So this MMF required for the air gap for silent pole machine can be found out using this standard equation. ATG is equal to 8 lakh BG kg LG. Gg is a gap contraction factor. Gap contraction factor. BG is the maximum flux density. Okay. LG is the length of air gap. LG is the length of air gap. So now MMF required for armature core, capital ATC is equal to ATC, this is ampere turn per meter multiplied by LC. LC is the length of flux path in the core. Okay. So ATC is ampere turn per meter corresponding to flux density in the armature core. Flux density in the armature core. That we have to find out. And from BH curve we have to see what is the ampere turns per meter according to that flux density. Then use this one and multiply with LC. This. Okay, you will get capital ATC. Similarly, MMF for teeth, ATT is equal to ATT into DS. This is depth of this slot. This is ampere turn per meter. So this is obtained from the BH curve. we should see what is the flux density in the teeth. Corresponding ATT in the from the BH curve we have to select and multiply with ds, we will get this one. Okay. Now coming to MMF required for armature core. Okay, this already we have discussed. And MMF required for pole body. Okay, in pole body, actually pole body flux is not constant. Okay, some flux is leaked, that is called leakage flux, and in some area both is full flux and leakage flux will be there. In some area leakage flux will not be there. So that is the reason we have to find out where is the flux density maximum, where is the flux density minimum. According to ATP max and ATP minimum will be there. So the ATP max you have to multiply with 1/3 of the height of the pole, that is HPL by 3, and ATP minimum we have to multiply with 2 HPL by 3. So corresponding to this ATP max and all that, ATP minimum we have to get it from the BH curve. So finally we can find out ATP. Okay, MMF required for pole body. And MMF required for rotor yoke, ATY is equal to ATY into LY. ATY into LY. So LY is the length of the flux path. So we can calculate using this equation. Okay. If we see the stamping dimensions and all that, so this is the rotor diameter, pole, 2 pole height from one top and 2 pole bottom, one height of the pole we have to subtract. Half of the dy in the top, half of the dy in the bottom. This is the dy, depth of the yoke. Okay. Now values of ATT, ATC are taken from BH curves of the material used. So total MMF can be found out using this equation. ATF naught is equal to ATZ, ATT, ATC, ATP, ATY. All these after adding we get ATF naught. Okay. Now design field winding of salient pole alternator. So we know this standard equation ATFL by ATA, that will be given where we have to select. The ratio should be 1.7 to 2. So where ATA is equal to this equation, use this equation to find ATA, substitute here, find ATFL. Okay, so once you know ATFL, so substitute here rho LMTF. Okay, EF is the total voltage, that is 80 to 85%, and divided by number of poles EF, and this cross sectional area of conductor can be found out. Okay, assuming density here. So now AF you have found out, density you assume, EF you can calculate, IF you can calculate. Once you know IF, number of turns can be found out. This is ATFL, turns and current, divided by current. So turns you will get. Once you get turns, actual resistance of the winding can be found out, substituting TF here. Okay. So now rotor design of turbo generator. So here the full load MMF ATFL is equal to 2 times armature MMF ATA. So ATA found out using this equation. Again, cross sectional area of conductor is found out using this equation. Okay. Now number of field turns can be found out using this equation. So IF is equal to delta F AF. Okay. Once you know IF, you can find out other parameters. So RF is equal to TF. So now once you know IF, you can find out TF here. TF into rho LMTF by AF, it will give RF. Actual field current IF is equal to EF by RF. So the number of field conductors can be found out using this equation, 2P ATFL divided by delta F AF. And conductors per slot is obtained using this equation, 2P ATFL delta F AF divided by SR. SR is the number of wound slots in the rotor. Okay, this is how to solve the problems of synchronous machine. Okay, so sometimes they will not give the winding factor. So we are supposed to find out winding factor. Winding factor nothing but Kw is equal to Kp multiplied by Kd. What is that Kp? Pitch factor. This is distribution factor. So how to calculate pitch factor? Using this equation, Kp is equal to cos alpha by 2. What is the alpha? Alpha is angle of short pitch. Sometimes they will give directly angle of short pitch. or you have to calculate using this equation. Slot angle multiplied by number of slots by which coils are short pitched. Okay, or sometimes alpha is equal to 180 degree minus actual coil span of the coil. Actual coil span of the coil, 180 degree minus actual coil span of the coil. And distribution factor KD can be found out using this sin Q beta by 2 divided by Q sin beta 2. So that where Q is the slots per pole per phase. Beta is the slot angle here. Beta is the slot angle which is equal to 180 by N. N is the slots per pole. N is the slots per pole. So now finally distribution factor KD is obtained using this equation. Sin theta PS by 2 divided by Q sin theta PS by 2Q. So what is theta PS? Theta PS is the phase spread that will be given in the problem. Q is the slots per pole per phase. Okay, we'll see now some of the problems, okay, and solutions for those problems. Now we'll see first problem. A simple problem. Determine the main dimensions of a 1000 kVA 50 Hz 3-phase 375 rpm alternator. The average gap flux density is 0.55 Weber per meter square and ampere conductors per meter are 28,000. Use rectangular poles and assume winding factor kWs 0.955. Bolted on pole construction is used for which maximum permissible limit permissible speed is 50 meter per second. The runway speed is 1.8 times the synchronous speed. Okay, this has been asked in 2019 and January 2020. So given data you note down. Okay, NS is given 375 rpm, Q 1000 kVA, F 50 Hz, B average 55.55 Weber per meter square, AC 28,000, kWs 0.955. Peripheral speed should not exceed 50 meter per second. Synchronous speed, okay, peripheral speed at runway speed is 1.8 times the synchronous speed. Runway speed whenever load is thrown off, so what is the maximum speed it achieves? Okay, so D and L we have to calculate. So this is the basic equation. Volume of machine is equal to Q C naught NS. So NS you find out 375 by R 60, 6.25 RPS, and C naught is equal to this P number of poles also you find out. Number of poles also you find out. Okay, this you find out, this you find out. Okay, so now C naught it comes out to be this 162. Substitute here. Finally D square L you will get. So for rectangular poles L by 2 ratio 1 to 5. Taking L by 2 is equal to 2. So this will come, L is equal to 0.393 D. So after that D comes out to be 1.36 meter, L comes out to be 0.34 meter. So peripheral speed VA is equal to this, it comes out to be 26.7 per meter square. Okay. So now peripheral speed at runway speed it is given 1.8 times, it comes out to be 48 meter per second. So for this simple bolted on pole construction can be used. Okay, bolted on pole construction can be used. So here L by 2 ratio, if you take less value, the speed will be less. Now coming to second problem, find the main dimensions of 2500 kVA 187.5 rpm 50 Hz, okay, 3-phase 3 kV Salient pole synchronous generator. The generator is to be vertical water wheel type. The specific magnetic loading is given 6.6 Weber per meter square, okay, 0.6 Weber per meter square, and specific electric loading is 34,000 ampere per meter. Use circular poles with the ratio of core length to pole pitch is 0.65. Specify the type of pole construction used if the runway speed is about 2 times the normal speed. Okay, this has been asked in the June-July 2018. Okay, this data I noted down. Q is equal to 2500 kVA, speed is 187.5 rpm, 50 Hz, 3-phase, 3 kV, BA is given, okay, AC is given, rectangular poles given L by 2 ratio. This is given. Specify the type of pole construction used if the runway speed is about 2 times the normal speed. Okay. Next we have found out d square L. Okay. For that d square Q by C naught NS. NS is about 3.125 RPM using this equation. Poles using this equation, it comes out to be 32. So now here C naught, substitute all those things. Okay, C naught comes out to be 214. Finally, find out d square L. So d square L is equal to 3.74 meter cube. So L by 2 ratio it is given. You can use this one to separate L and D. So finally, we will get D is equal to 3.89 meter, that is 3.9 meter. L is equal to 0.247 meter. So once you find out this D and L, peripheral speed VA is equal to pi D NS. D substitute here. So VA comes out to be 38.29 meter second. This is normal peripheral speed at normal condition. Okay. The runway speed, okay, that should be, it should not exceed, that should be equal to 2 times VA, 2 times this one. That comes around to be 80 meter per second. 80 meter per second. Okay. So and therefore dovetail construction with T head can be used. You cannot go for bolted on. Bolted on only it can stand up to 50 meter per second. So here runway speed is 80 meter per second. So for that dovetail construction with T head can be used. Okay. Now coming to third problem, find the main dimensions of 100 MVA, 11 kV, 50 Hz, 150 RPM, 3-phase water wheel generator. The average gap density is this 0.65 bar per meter square, and ampere conductors per meter are 40,000. The peripheral speed should not exceed 65 meter per second at normal running speed in order to limit the runway's peripheral speed. So this has been asked for twice. Okay. So given data Q is equal to this, F is equal to this, synchronous speed this. Okay, 150 RPM here. AC given 40,000, B average is given. That VA should not exceed 65 meter per second. So now volume of machine can be calculated using this equation. So NS we have to find out. NS is equal to 2.5 RPS. Okay. Now C naught we have to find out. Substituting V average, ACA, KWS. So we get 274. Number of poles is required. So we will get 40 here. 2F by NS. So d square L is equal to, we will get 146 meter cube. Okay. So now for circular poles, L by 2 ratio is 0.6 to 0.7. So what we will do, we will take L by 2 ratio 0.65. So we get L is equal to this one. From this D is equal to 14.2 meter, L is equal to 0.724 meter. Okay. Now you see D and L we have found out, but we have to check the this for proper diameter. So peripheral speed is equal to, at synchronous speed is equal to VA is equal to pi D NS. So substitute here VA pi D NS. This comes out to be 111.52 meter per second. Okay, but allowable maximum permissible value is 60 meter per second. So we cannot use round poles. We cannot use round poles. Okay. So now coming to if you go, you can go for rectangular poles. Okay, use rectangular poles. L by 2 ratio 1 to 5. So select L by 2 ratio is equal to 4. So L is equal to 4.2. Substitute here L is equal to 0.314 D. From this D and L, if you separate, D comes out to be 7.75 meter. L comes to be 2.43 meter. You can see here this D and this D. Okay, this D and here this D. Here D has come out now. So peripheral speed will be less. PA peripheral speed comes out to be pi D NS. This comes out to be 60.86 meter per second. So which is below 65 meter per second. So rectangular poles are used. Rectangular poles are used. So here maximum permissible limit here it is around 65. Okay. So this is how to select the types of pole. Now coming to this is fourth problem. So 1000 kVA, 3300 volt, 50 Hz, 3000 RPM, 3-phase alternator has 188 slots with 5 conductors per slot. Okay, 5 conductors per slot. So 180 slots given. Single layer winding with full pitch coil is used. Winding is star connected with one circuit per phase. Determine the specific electric and specific magnetic loading. If the stator bore is 2 meter and core length is 0.4 meter. Using the same loadings, determine the corresponding data for 1250 kVA, 3300 volt, 50 Hz, 250 RPM, 3-phase star connected alternator having 2 circuits per phase. The machines have 60-degree phase spread. Okay, this has been asked in June, July 2019. So given data for 1000 kVA that you note down, 1000 kVA, line voltage 3300 volt, F is 50, NS is synchronous speed 300 RPM, number of slots A180, conductor post slot 5, single layer full pitch winding, diameter 2 meter, L 0.4 meter. We have to find out B average and AC. So using B average, okay, this again what he has asked, using same B average, calculate the above for 1250 kV generator. Okay, EL. This is also part of the problem in this one. Okay, so using after finding out B average and AC above, okay, and for 1250 kVA generator, find this data he has given. Okay, EL, this one is use that data B average and AC for this generator. Okay, NS 250 RPM, 3-phase star connected alternator having 2 circuits per phase. The machines have 60-degree phase spread. Machines have 60-degree phase spread. So we have EPH is equal to this 4.44 F TPH by a KW. So when machine KW he has not given. So when he gives phase spread 60 degree, so we are supposed to calculate KW. Okay, there are formulas are there that we have discussed. The flux is equal to B average into A. So B average is equal to flux by A. So now to find TPH, total number of conductors is equal to total number of slots per conductors per slot. So 180 slots, conductor plus per slot is 5. So total number of conductors is 9. So turns per phase, total conductors divided by 6. 6 TPH is equal to total number of conductors. So 150. Okay. So synchronous speed 5 RPS. Okay. And KW is equal to KP into KD. Here KP it is full pitch winding. KP is equal to 1. So now I told KD, we have to find out KD is equal to sin theta PS by 2, Q sin theta PS by 2Q. Q is the pole number of slots per pole per phase. Theta PS is the phase spread. Phase spread is 60 given. Q is 3 given. Finally, we will get this KD is equal to 0.96. So slots per pole per phase Q is equal to 180 by this is 3 into 20. Okay, per pole, this is per phase. Total number of slots. This comes out to be 3. 3 I have substituted here. Okay. So KW is equal to 0.96. So EPH is equal to, this is the equation. Okay. Here parallel path A is equal to 1. So from this pi can be calculated because TPH we know, KW we know, F we know, EPH we know. So pi we can calculate. Flux. So flux comes out to be 59.6 into 10 raised to minus 3 Weber. So B average is equal to flux by area. So flux by tau L, pi dl by P, this is the area, pi dl by P is the area. So that comes out to be 0.474 Weber per meter square. Okay, B average is equal to 0.474 Weber per meter square. Okay, P here we have substituted 120 by NS, 20 we have substituted. That has been calculated using this. So now star connected power is equal to 3 EPH, IPH into 10 raised to minus 3. Minus 3, 10 raised to minus 3 because this right hand side Q is in kVA. So IPH is equal to Q by 3 into EPH. So this is 1000, 10 raised to minus 3. If this comes this side, 10 raised to 3, 3 EPH. Okay, this is 3 kVA by root 3. So it comes out to be 17.5 amps. 17.5 amps. So since there is only one circuit per phase, IZ is equal to IPH. So sorry, this is 175. Okay, 175. This comes out to be 175. Okay, so now specific loading AC is 6 IZ TPH by pi d. So this comes out to be AC is equal to 25,000 ampere per meter. So finally peripheral speed is equal to pi d ns 31.4 meter square. So now whatever the data B average AC we got in this problem, we have to use it for 1250 kVA and find the dimensions D and L. So kW we have found out in the previous this one part 0.96, B average is this 0.474 ever per meter square, AC is 25,000, Q is 3. So now this is the volume of machine is equal to Q by C naught Ns. Ns is 4.167 RPS. Now C naught we have to find out. Okay, in this you substitute kW here, B average here, AC here. So C naught comes out to be 125. Okay, P comes out to be here 24. Now D square L is equal to, substituting this all those values, 2.4 meter square. So now keeping the same peripheral speed, this is peripheral speed previously we got. Okay, peripheral speed is equal to what? V is equal to pi d into 4 point this pi d ns, pi d ns. So keeping the same speed. Okay, this d we can find out. D we can find out. So now what is that? D is equal to 2.4 meter. D is equal to 2.4 meter. So then L is equal to, from this once you get 2. D is equal to this one. So this you can get 2.4 by, this is 2.4 meter cube. Okay, this is meter cube. Okay, this is 2.4. So this comes out to be, this is D square. D is 2.4 square here. So this comes out to be 0.416 meter. So D and L we have found out. Now EPH is equal to this. Okay, so here in the second part, A is equal to 2. A is equal to 2 here. Okay, so now B average is equal to this. For B average, this one, pi dl by P, pi dl by P. Okay, so now flux comes out to be this. Flux comes out to be this. Now TPH is equal to, using this option, in this A is equal to 2 in this for second problem. Okay, so now TPH comes out to be 288. So number of conductors is equal to 6 TPH, this one. So number of slots is equal to 3 PQ, this one. So conductors per slot is equal to 8. So these all the data we have found out. Conductors per slot, this TPH, number of slots, B average, and this is B average. Okay, no, previous data only we have diameter and L we have found out. TPH we have found out for this machine. Okay. This problem is almost same. Okay. Suitable number of slots, conductors per slot, everything is same. Only thing is that in this problem, he has given what? Okay. The flux density in the gear should be the maximum flux density he has given. Instead of the average, maximum he has given. It is 0.9 Weber per meter square. Okay. To find out average flux density from maximum, we have to multiply 2 by pi with maximum. So we will get average flux density. Rest is same here. Rest is same. Just see, go through this problem and okay. Pi we have calculated here. Okay. TPH we have calculated here. TPH comes out to be 124. But for this, for 3.3 kVA machine, slot pitch should be around 40 mm. This is important factor that you should remember. So number of slots is equal to 3 PQS. Okay. Now slot pitch is equal to pi d by SS. Pi d by SS. SS is the number of slots. Okay. So now QS is equal to pi d by 3 P YS. This comes out to be slots per pole per phase, this one. Okay, so if you substitute here, it comes out to be 3. So total number of stator slots is equal to 183 PQS. So total number of stator conductors comes out to be, this is 744. So conductors per slot 744 by 180, 4.13. It is rounded up, okay, to 4. So total number of actual conductors is equal to 720. Actual turns per phase is equal to 720 by 6. It is 120. Okay. So now this is another type of problem. A 500 kVA, 33 kV, 50 Hz, 600 RPM, 3-phase Salient pole alternator has 180 turns per phase. Estimate the length of air gap if the average flux density is 0.54 Weber per meter square. The ratio of pole arc to pole pitch is 0.66. The short circuit ratio is 1.2. The gap contraction factor is 1.15. And the winding factor is 0.955. The MMF required for the gap is 80% of the no load field MMF. Okay. So what we have to estimate the length of air gap. So data TP is given, 500 kV, 33 kV, 50 Hz, NS 600 RPM. B average is this. So pole arc to pole pitch, this ratio KF or psi is equal to 0.66. SCR is 1.2. kg is 1.15. KW given 0.955. ATG is 80% of ATF naught. Okay, ATG is this repeated. Okay. Now LG we have to find out. LG we have to. So now ATG is equal to, this is the basic formula. So ATG is equal to 0.8 ATF naught, where ATF naught is equal to this. So ATA you find using this equation. For this P unknown, P found out, P is equal to 10. Okay, then IPH I want. So IPH I can find out using this equation. Okay, these are the equations. Already we have discussed several times. IPH comes out to be, it is 1.478. So ATA you can calculate. So ATF naught you find out. SCR 1.2 given. ATA you substitute here. ATF naught you got. Once you get ATF naught, see this is the ATF naught. Substitute here, ATG you find out. So this ATG you know, this you know, this you know, LG can be, this which is unknown can be found out. So now BG, this is the maximum, this one, B average by KF. So because in this equation, this is the BG, okay, that you have to find out, 0.818 Weber per meter square. So ATG is equal to 0.8 ATF naught, this comes out to be this. So now this is the basic equation, okay, this is unknown, okay, BG we have found out, KG we given, ATG we have found out, so LG is equal to this. So substitute here all these things, so LG comes out to be 5.22 M. Okay, so now this is another problem. Problem 7. The following is the design data available for the 1250 kVA, 3-phase 50 Hz, 3300 volt star connected, 300 RPM alternator of salient pole type. Stator diameter 1.9 meter, stator core length L 0.335 meter, pole out to pole pitch 0.66 turns per phase, 150, single layer concentric winding with 5 conductors per slot. Short circuit ratio 1.2. Assume that the distribution of the gap flux is rectangular under the pole arc with 0 values in the interpolar region. Okay, assume that the distribution of the gap flux is rectangular under the pole arc with 0 values in the interpolar region. So calculate specific magnetic loading, armature MMF per pole, gap density, air gap length. Okay, MMF required for air gap is 0.88 of no load field MMF, this is given, and gap contraction factor is 1.15. Okay, so B average we have to find out, ATA we have to find out. Okay, gap density over pole arc we have to find out, and air gap length MMF required for MMF air gap length we have to find out LG. Okay, what is given here, MMF required for air gap is 0.88 of no load field MMF. Gap contraction factor is given. So data 1250 Q is equal to 3-phase 50 Hz, line voltage given, star connected, NS is given, D is given, L is given, psi is given, TPH is given, ZSS is given, SCR is this. So now flux distribution is rectangular. Okay, this is important. What is the B average we have to find out? ATO we have to find out, BG we have to find out. ATG is given 0.88 times ATF naught, KG is given. So to find B average is equal to pi by A, where A is equal to pi dl by P. So P we have to find out using this one. P comes out to be 20. So now area comes out to be 0.1 meter, pi dl by P. Okay. Now here we don't know pi. Okay. So but we know this equation. EPH is equal to this. So this we know, this we know, this we know, this we know. So Kw is equal to Kp into Kd. Kp is full pitch. Coils are used. And here in the problem given that distribution of gap flux is rectangular under polar, that is given. So if the distribution of the gap flux is rectangular under polar, the phase spread is taken as theta ps is equal to 60. This is important assumption. Okay, this you should remember. So using this you find out Kd. Okay, now Q is unknown. In this one Q is unknown. This theta ps is 50. Again Q is loss per pole per phase. So how to find out Q? TPH is 150. Okay, total number of conductors is 6 into 150, 900. 900. So conductors per slot 5. So total number of slots. Total number of slots. Okay, 5 by 9. Total 9 turns conductors divided by conductors per slot. So total number of slots comes out to be 180. So slots per pole per phase 180 divided by 20 into 3. This comes out to be 3. Q is equal to 3. Substitute in this equation. Kd comes out to be this 0.96. Now Kw is equal to Kp into Kd. This is 0.96. So substitute here 0.96 is in this equation. You get pi is equal to 59.60 into 10 raised to minus 3. So specific magnetic loading B average is equal to pi by A. This comes around to be 0.596 Weber per meter square. So gap density over polar, that is B average by psi. So that comes out to be Bg is equal to 0.903 Weber per meter square. Now ATA is equal to this equation. We are about to find out ampere per pole. Okay, ampere turns per pole. So this we don't know IPH. Okay, so IPH we have to use this equation. So many times we have done the method. IPH is around 218.70. So ATA comes out to be 4252 amps, 4252 amps. So now no load MMF is given as SCR into ATA. SCR is given 1.24252. So ATF naught is this. But in the problem it is given ATG is 0.88 times ATF naught. Ampere turns required for the gap is equal to 0.88 times ATF naught. So this comes out to be ATG is equal to this much. So substitute here. Okay, this we know, find LG. Find LG. So LG comes out to be 5.44 mm. Air gap length is 5.44 mm. So now here problem. So 8250 kVA, 3 phase, 50 Hz, 3300 volt, 300 RPM synchronous generator with a concentric winding has following data. B average is equal to this. AC is 33,000, gap length is 5.5 mm, SCR is 1.2, and field turns per pole is 60. Effective gap area is 0.6 times actual area. Peripheral speed is 30 meter per second. Find stator core length, stator bore, turns per phase, MMF for air gap, armature MMF for pole, and field current for no load and rated voltage. Okay, so data solution is data Q is given 1250 kVA, 3 phase, 50 Hz, 3300 volt, NS 300 RPM. B average is given, AC is given, LG is given, SCR is given, TF is given, effective area is 0.6 times A. VA is, that is 30 meter per second. L we have to find out, D we have to find out, TPH we have to find out. Okay, that is fields turn per pole. Okay, ATG we have to find out, ATA we have to find out, IF we have to find out, IF we have to find out. So to find out D and L we have to use this equation. Okay, NS is 5 RPS, C naught is this much. So this KW is not given, we have to assume this one. So C naught comes out to be 201, and this factor he has given, VA is equal to pi D in S. Okay, 30 he has given, we have to use this one. Because L by tau ratio we don't know, so use this criteria. D is equal to VA by pi ns, that comes to be D is equal to 1.90 meter. Okay, so this D is you substitute here, find L. L comes out to be 0.345 meter, so this is D 1.90. So to find TPH again we have to use this equation. Okay, again this TPH is unknown, pi is unknown. So pi you find out using this equation. Okay, so this comes out to be, pi comes out to be this one. Pi comes out to be this one. Okay, again here I have found out P. Okay, this area is this much. So flux per pole will be 59.74 into 10 raised to -3 Weber. So substitute in this one, this pi, find out TPH. So here TPH comes out to be 150. Okay, so now ATA is equal to 2.7 IPH, TPH, KW divided by P. TPH we know, IPH we don't know. Again we have to use this equation to find out IPH. So IPH comes out to be 219 amps. So this you substitute here, IPH. I have substituted here. ATA comes out to be 4235 amps. Okay. Now given that effective area of pole is 0.87 actual area. Actual area is this. This is the effective area. So effective gap density is equal to kg into bg. Kg into bg. Pi by effective area. So this pi divided by effective area. This kg bg is equal to 0.966 Weber per meter square. Effective gap density. So now ATG, that is MMF per air gap, is equal to 8 lakh kg bg lg. Kg bg lg. So substitute all these things. ATG will get this one. MMF per pole at no load, ATF naught is equal to SCR into ATA. So SCR is 1.2, ATA is this much. So ATF naught you got. So field current IF is equal to ATF naught by TF. So ATF naught is this. So 85 amps. This is how to find out field current IF. Okay. Now coming to ninth problem. Here a 2500 kVA, 225 RPM, 3 phase, 60 Hz, 2400 volt star connected salient pole alternator has following design data. Diameter is given, core length is given. Okay, slots per pole, QS is given, 3.5 conductors per slot given. Circuits per phase 2, leakage factor CL, okay, 1.2, winding factor 0.95, KW given. Flux density in the pole core is 1.5 Weber per meter square. The winding depth is 30 mm. The ratio of full load field MMF to armature MMF is 2, ATFL by ATA. Field winding space factor is 0.84. Okay, and field winding dissipates 1108 watts per meter square of inner and outer surface without the temperature is exceeding the permissible limit. Leave 30 mm for insulation, flanges, and height of pole shoe. Height along the height of the pole. Find the flux per pole, length and width of the pole, okay, winding height, pole height. This is all about field design. Flux per pole, length and width of the pole, winding height, pole height. Given data this one, okay, 2500 kV, NS is this, F is this, VL is this, star connected, D is this, L is given, Q 3.5 given, Z is 4, A is equal to 2, Kg 1.2, KW 0.95, BC 1.5 Weber per meter square, DF 30 mm, AFL by ATA 2, SF 0.84, QF 1800 watts per meter square. Okay, yeah. Flux we have to find out, BP we have to find out, LP we have to find out, HF we have to find out, HPL we have to find out. So this has been asked twice. Okay. Now to find the flux per pole, EPH, this equation we have to use. Okay. So now poles are here. This is KW. Okay. TPH, this one. So NS is equal to this. Poles will find out. Later it is useful. So number of slots is equal to 3PQ. 3 into 32. This comes out to be 336. Now total number of conductors. So number of slots is this. Total number of this is conductor per slot. So this will give total number of conductors. So 336 into 4. This comes out to be this one, and this also equal to 6 TPH. Okay, turns per phase. Now if turns per phase is equal to 1344 by 6, 224. Because here we don't know turns per phase, so that's why we should find out turns per phase. It comes out to be 224. So phi is equal to, from this equation, this is unknown thing. EPH is 2400 by root 3, because this is star connected, so we have to divide it by root 3. This is A is equal to 2 here, 2 parallel paths. So this phi comes out to be 48.89 into 10 raised to minus 3. Okay. Now to find pole body details. So area of pole body, AP is equal to pi p by BP. So pi p is equal to CL into phi. This flux per pole we have found out, multiplied by leakage coefficient. So this is pi p. So therefore, if BP we know 1.5 Weber per meter square, area of the pole you can find out. Okay. So length of the pole body LP is equal to length of the armature core. So LP is equal to 0.44 meter. So now this length into breadth is equal to AP. So AP we know. So now breadth we can find out. So breadth is equal to AP by LP. So width of the pole is equal to this one. It comes out to be 0.089 meter. Now to find out HF, ATFL into 10 raised to minus 4 divided by root of SF, DF, QF. So this we know, all given. ATFL we don't know. We should find out ATFL. Okay. ATFL is equal to what? 2 times ATA. So what is it? ATA? ATA is, can be found out using this equation. 2.7 IPH by A, TPH, KW by P. Okay, we don't know IPH. Again we have to find out IPH. Substitute here, you can find out ATA. Okay, once you find out ATA, then calculate ATFL, substitute here, you can find out HF. Okay, so again this is using basic equation. I have found out IPH, it comes out to be 601 amps. Substitute here, ATA you find out is 5396 amps you will get. ATFL, it is 2 times ATA, 10,792. Substitute here, you get HF is equal to 0.16 meter. Okay, but 30 mm they have given. Okay, so add this one. So height of the pole is equal to 0.19 meter. 0.19. So now coming to 10th problem. So here the field coils of Salient pole alternator are wound with single layer winding, bare copper strip 30 mm deep, with separating insulation 0.155 mm thick. So determine the suitable winding length, number of turns, thickness, and conductor to develop an MMF 1200 amperes with potential difference of 5 volt per coil and with a loss of 1200 watts per meter square of total coil surface. The mean length of turn is 1.2 meter. The resistivity of copper is 0.021 ohm meter and mm square. This is regarding the field design of this one field system. Okay, this is similar to shunt field winding. ATFL given 1200 amps. Length of mean turn 1.2 meter. Rho is this. Depth of the field winding 30 mm. EF is voltage across each field winding is 5 volt. HF we don't know, TF we don't know. So depth of the conductor, okay, DC, or height of the conductor, DC. Okay, what is that we have to find out. This can be obtained once you find out the cross-sectional area of the conductor. Okay. Now area of the field conductor AF, this is the basic equation. So area you can find out using this one. So height of the conductor, that is thickness of the conductor, area divided by depth of the conductor. Okay, this height of this, because area equal to depth and height. Both you have to multiply. So depth of the conductor we know 30 mm given. Height of the conductor can be found out using this equation. Area divided by depth, 2 mm square. So area of the conductor is equal to 60 mm square. So loss dissipated QF is equal to QF specific dissipation multiplied by surface area. So heat dissipating surface area is found out using this equation. Using this equation, S is equal to this. S comes out to be this. Now loss dissipated QF is equal to 1200 into S. This is so QF is equal to this. Field current IF is equal to this is watts divided by loss divided by EF. So this comes out to be this. So therefore IF is equal to this equation. If we divide this one, it comes out to be 576 HF into 17.2 this one. But field MMF is equal to IF into TF. So this is IF multiplied by this is IF TF. This is equal to this field MMF. Okay. So now height occupied by each conductor is 2 into 0.15. This is mm. So now height of the winding HF is equal to, okay, this is 2.15 mm. Okay, TF number of turns multiplied by height of each conductor. Okay, this we got. Since it is single layer winding, so this total height depends upon number of turns multiplied by height of the each turn. So substituting this, we will get this one. Okay, substitute here. Okay, HF is substitute here. So in this equation, HF you substitute. So you will get after solid this equation in terms of TF. So TF will get 92. Okay, this is quadratic equation. One will get 92, another value this. This is minus. This is neglected. Okay. Finally, HF is equal to 2.1 times TF, 197.8 mm. Okay, this is how to find out height of the field winding. Now coming to last problem. During the design of three-phase 7.5 MVA, 6.6 kVA, 50 Hz, 3000 RPM turbo generator, following information have been obtained. The gross core length is 0.9 meter, internal diameter is 0.975 meter, number of stator slots per pole per phase is 7, sectional area of the conductor is 190 mm square, number of conductors per slot is 4. So calculate flux per pole, specific magnetic loading, specific electric loading, current density for the stator winding. So this has been asked in July 2017. Okay, data this. So this is MVA. Okay, this is MVA. Okay, this is MVA. 7.5 MVA, 6.6 kVA. This 3000 RPM. D is equal to this. L QS. ES is equal to this. ZS is equal to this. Pi we have to calculate. B average we have to calculate. AC we have to calculate. Delta we have to calculate. So here pi is equal to B average by 2L. 2 into L. B average, this is B average into pi dl by P. So P is unknown. So from this equation P is found out is equal to 2. So now we can find out. So now here EPH is equal to TPH. TPH is unknown things. Okay, this can be found out using this one. Conductor per slot 4. So total number of slots, Q slots per pole per phase given 7. Total number of slots per phase. So per pole is not there. We have to multiply with the number of poles. 7 into 2, 14. So total number of conductors per phase. 14 into ZSS. 14 into conductors per phase here. 56. So turns per phase TPH is equal to 56 divided by 2. 28. Assuming full pitch coil, a stator winding KW is equal to 0.955. So now pi is equal to this one star connected. Okay, KW is 0.955. TPH we have found out 28. So pi comes out to be this. So now B average is equal to pi by pi dl by P. So this comes out to be 0.605 Tesla. And coming to specific electric loading, we have this equation. Okay, we have this equation d square lns. Ns is equal to this. C0 is equal to Q by this. So find out C0. 296. Okay. Now in C0, in the C0, this you know. Okay, this we don't know. This we know. So now this from this AC we can find out C0 divided by this. So C0 296. Rest you substitute here. This comes out to be around 46,573 ampere conductor per meter. And to find the current density, IPH is equal to this 7.56 into 10 raised to 6, root 3, 6.6 into 10 raised to 3. This comes out to be 656 amps. So current density is equal to IPH by AS. IPH by AS. So 656 by 190 amps per 3.45 amps per mm square. Okay, this is what about synchronous machine. So problems, what you have to do, you have to practice. Okay, so just read the problems carefully. What is the data given? What has to be calculated? According to, you just select the equations and solve it. This finishes the module 5. Okay, thank you.